A small block with a mass of 350 grams, so right away we have an issue, right? We have to convert that to kilograms, starts from rest at the top of an incline. It slides without friction down the incline, around the inside of the loop, and then continues on. The height of the incline is 110 centimeters. Oh, there's another conversion. And the radius of the loop is here. That's another conversion. Find the initial potential energy of the block. Find the velocity of the block at the bottom of the loop. Then find it at the top of the loop. And then what is the normal force on the block at the bottom of the loop and then at the top of the loop? The initial potential energy is when the block is at the top of the incline. Since it is at rest, all of the energy is GPE. There's no kinetic energy, there's no elastic potential energy. So we'll want to use the GPE equation, which is equal to mgh. Now our problem here gave us grams and centimeters. So we use unit conversion here. 350 grams times 1 kilogram over 1,000 grams. And it's called unit conversion because this thing here is equal to 1. It's a unit. And we get 0.350 kilograms. For centimeters, there's 1 meter has 100 centimeters. Think of it in a century, which sounds like centimeter. It's 100 years in a century, same thing. And there's other ways to remember it, but that's how I always do it. You multiply through, and you get a GPE of 3.77 joules. Find the velocity of the block at the bottom of the loop. We're going to use conservation of energy for these problems. There are no external forces acting on the block. An external force would be friction. We don't have any friction here, so we can use conservation of energy. At the top of the track, all of the energy is in the form of GPE. So E0 will be GPE. At the bottom of the track, which we've arbitrarily set, GP is equal to 0. And the GP above will be, of course, mgh, where h is the height above that point. So all the energy at the bottom is kinetic energy. So here's our work energy equation. E0 plus work is final energy. We're leading up to the conservation of energy. Work we've just said is 0. There's no external forces doing work. So the initial energy is GPE. Work is 0. E final is KE. So what do we have? GPE equals KE. We then substitute in the equations, and mgh is equal to 1/2 mv squared. Now, why don't we just say 1/2 mv squared is equal to the GPE we found on the previous slide? Well, we could do that, but we've already calculated that and rounded off, so we'd like to be a little more exact. And what's cool about this one here, when you set this equation, m's go away, okay? They cancel, so it's a very simple expression. Here's our equation, and look at that. Mass doesn't matter for the velocity. We divide it right out. So we get this, then we switch sides because we're solving for velocity. Then we'll multiply both sides by 2, and then finally take the square root. You get this really neat little equation. The velocity is the square root of 2 times the gravitational acceleration times the height. Put in the numbers, and the velocity at the bottom is 4.64 meters per second. Now we need the velocity at the top of the loop. So when we started, the block only has a height. It's not moving. When it comes here and goes up to the top, it has both a height and a velocity. It's still moving. So we're going to use conservation of energy again. There are no external forces, so the work will go out. That's equal to 0. And this time, there's 2 forms of energy at the top of the loop. We have GPE and KE. So we have our initial energy is GPE up the ramp. We're going to call that ramp now. Could have called it incline, but for some reason I changed it to ramp. And that's going to equal the final energy, which is the kinetic energy at the top of the loop and the GPE at the top of the loop. So we have GPE ramp is KE at the top of the loop plus GPE at the top of the loop. Find the velocity of the block at the top of the loop. The first trick we have to avoid, or trap for that matter, is the height of the loop. We were given the radius of the loop, but don't use that because how high is this guy? The block is twice the radius. It's the diameter of that loop. So we have to substitute 2 times r loop in for h. So here's our conservation of energy equation. And like we just said, we substitute 2r loop in for h loop. Now, what do you notice about the equation? It has m's in every single expression there, so we cancel out the m's, and we have this. Now, we're going to subtract g times 2r loop from both sides, so we get everybody with g on the same side here. Now, we're trying to solve for velocity, so we're going to switch sides. So we have 1/2 velocity squared loop is equal to gh minus g times 2 times r loop. Can I do anything? Yeah, you always like to factor. It reduces the amount of multiplication you do. So we take the g out in front. We then multiply both sides by 2 to clear that 1/2. And finally take the square root of v squared, and this is our expression that we will plug numbers into. And here is why algebra is so beautiful when you work with physics. We found that the velocity at the top of the loop is this expression here. Doesn't that look familiar? Here's the velocity of the block at the bottom of the loop. We have height here. That's the height of the incline. That's this right over here. That's the height there. And we have height here also. But what's different about the top of the loop? Well, we subtract out this distance here. Okay, so we're actually finding the difference in potential energy between the top of the incline and the top of the loop. And where does that GPE go into? It goes into kinetic energy and velocity. So we've replaced h with h minus 2r with this term here, right? Okay, let me just be a little clearer. Here's 2r. This whole height here is h. So this piece, which is the difference in height between the top of the circle and the top of the incline, is h minus 2r, which is that equation there. So now, finally, we've done all the interesting work. Now it's kind of anticlimactic. We just put the numbers in, make sure you do the math right, get the units, and velocity at the top of the loop is 3.96 meters per second. When the box is at the top of the loop here, some of the energy is in the form of kinetic energy plus GPE. That means all the initial energy here did not just go into the kinetic energy like it did when they were at the bottom of the loop. That means the kinetic energy up here is less than the kinetic energy at the bottom. And that got proved out by our calculations. The top of the loop, the box's velocity, was 3.96 meters per second, while at the bottom it was 4.64 meters per second. What is the normal force on the block at the bottom of the loop? Once you hear force, we're into dynamics. Once you're into dynamics, you're into a free body diagram. The box has experienced circular motion. It's going around the loop. And since it is still in the loop, we will need to consider what? Centripetal acceleration, not linear. So here's our free body diagram right over here. At the bottom, you've got gravity pulling you down. The normal force is pointing up, opposite gravity, and the acceleration is in the up direction because the acceleration always points towards the center of the circle. So if you're at the bottom of the circle, the acceleration points up. Newton, sum of the forces is ma. We have a positive sign for normal because it's up, negative for mg because it's down, and positive for ma because it's up. And since we're in circular motion, the acceleration is v squared over r, where v is the velocity at the bottom of the loop. So we have normal minus mg is mv squared bottom over r. Let's do the algebra. And notice we didn't put the sketch on this slide. It's not just to save space, but it's to just show the importance of once we have the free body diagram, we don't care what it looks like. Well, we care what the free body diagram looks like. We don't care what the sketch looks like anymore. So we have our normal minus mg is mv squared over r, where v is v bottom. We add mg to both sides. That's this step here. And once again, let's factor m out so we can do less multiplication at the end. And we have m times g plus v squared over r. We're given m. Here's one of our constants, g, 9.8 meters per second squared. Here's the velocity that we calculated earlier in part B. And here's the radius. So now we actually use the radius of the loop, not the diameter. We don't have to double it here. And we get a normal force of 53.7 newtons. Now we're at the top of the loop. Let's find the normal force. Key, of course, is the free body diagram. This time, since you're on the inside of the loop here, the track is pushing you down. You have a normal force down. Gravity, of course, is down, and the acceleration is towards the center, which in this case happens to be down. And you might say, well, what if the loop were on the top? Excuse me, the block were on the top of the loop. Well, if you didn't have anything holding it to the track like they do with roller coaster rides, it'd go like this, and then it's in projectile motion, but that's a problem for another day. Here's our equation, sum of the forces. This time I'm skipping the a because we know it's just mv squared over r. We have circular motion. Normal is down, mg is down, and ma is down. So we have all negative values for our forces in Newton's second law. Okay, so here's our equation, and we're going to go through some algebra. First thing is nobody likes working with negatives, so multiply everything by -1. See, isn't that a lot nicer? And then we'll subtract mg from both sides so we can isolate the normal force. Once again, factor out m, and now I have m times minus g plus v squared over r. Substitute in all our values, and this is like the last 5% of the problem. Now be careful. Make sure you use the velocity we found for the top of the loop, not the bottom. We're at the top now. And you get 46.8 newtons.